Welcome to GPT Learning Hub, where we simplify complex ML concepts. This video is going to be a comprehensive course in deep learning, the subset of machine learning focused on neural networks. It's broken up into sections, so feel free to skip around if needed. Here's our outline. First, the math you need for ML. Second, gradient descent. Third, linear regression. Fourth, a linear regression quiz. Fifth, neural networks 101. Sixth, coding neural networks. 7th, PyTorch 101, 8th, NLP 101, 9th, how LLMs learn, 10th, self-attention. A bit about myself, I'm a final semester master's student studying machine learning. At the start of 2024, I released a free machine learning platform with my colleague Navdeep, who created NeetCode. Later on, Grant from 3Blue1 Brown endorsed our resource, and we've gained a ton of users since then. You can check out the platform at the link in the description. Feel free to share this video with a friend that might find it useful. Without further ado, let's get started with this course. It's actually a misconception that you need a crazy amount of math for ML. You can get started with a basic understanding of matrix multiplications and derivatives from calculus. That means you should understand how to find the derivative of functions like this, but don't worry about functions like these. Also, you may have heard before that complex ML models just boil down to matrix multiplication. While this is a bit of an oversimplification, there's also plenty of truth to that. Consider a large language model. Here's how they generate text. The prompt is passed in, and the output is the word that's most likely to come next in the sequence. This word is concatenated to the input sequence, and the next word is obtained. Concatenate again, and the process repeats. LLMs are just large autocomplete models that we can iteratively invoke. But to actually understand the internals of this black box, we have to dive into matrix multiplications and some basic derivatives. Let's go over a few quiz questions that cover the essential math for ML, and then after you finish the quiz, I recommend checking out my step-by-step machine learning roadmap, which consists of over 25 video modules and practice problems. It's completely free, and you can grab it from the link in the description. Let's get started with the quiz. Question 1. Given two matrices, what is the shape of the product? Understanding the dimensions of matrix multiplication is actually important for implementing models, since libraries like PyTorch require you to specify these dimensions when instantiating components of a model. If you want to skip directly to the answer, the timecode will pop up now. Okay, we have a 4x6 matrix on the left and a 6x4 matrix on the right. The first rule to check is whether this matrix multiplication is possible. The number of columns in the first matrix needs to match the number of rows in the second matrix. If these dimensions are unequal, then the output is undefined. When we get to the question on how to actually multiply two matrices, this rule will make sense, but for now let's just accept it. Okay, so the matrix multiplication is defined. The shape of the product is another simple rule. Let's take the number of rows in the first matrix and the number of columns in the second matrix, and those will be the output dimensions. For the actual multiplication, we'll pair up every row in the first matrix with every column in the second matrix. The answer then is 4x4. This might be unsatisfying, so let's move on to the next question, which asks us to actually perform the multiplication. If you want to skip directly to the answer, the timecode will pop up now. We have 3 columns in the first matrix and 3 rows in the second matrix, so the output is defined and will also be a 3x3 matrix. The only phrase you need to remember for matrix multiplication is row column. To get the top left entry, we multiply the first row with the first column. This means multiplying the corresponding numbers and adding them up. To get the other entries in the output, we keep following the row column rule. First row, second column, and we get the second entry. First row, third column, and we get the third entry. Second row, first column, and we get this entry, and so on. This also explains why the number of columns in the first matrix needs to match the number of rows in the second matrix. The number of columns in a matrix is just the number of entries per row, and the number of rows is just the number of entries per column. This might seem abstract right now, but remembering the phrase row column will be very helpful in understanding self-attention, the crux of transformers and large language models. That video is linked in the description if you're interested in learning about attention next. Question 3. At what value of x does this function have a positive slope? Understanding basic calculus is important for gradient descent, the algorithm behind training. We can look at a line tangent to the function at 3 points, x less than 0, x equal to 0, and x greater than 0. Only when x is greater than 0 does this line have a positive slope, So the answer must be x equals 3. This might seem simple or obvious, but it's actually critical to visually understanding gradient descent, the first ML algorithm everyone should learn. That video is linked in the description if you're interested in watching it next. Lastly, question 4. How many derivatives does this function have? This is actually important when minimizing a function during training. To find the minimum of a function, we adjust the values of the inputs, in this case x, y, and z. In gradient descent, the derivative of the function, with respect to each input, is used to minimize the function. That's one derivative for each input for a total of 3 derivatives. And that wraps up our short quiz. If you've made it to this part of the video, then I think you'll enjoy our ML community. I offer weekly lectures, one-on-one mentorship, and a few special bonuses. If you're interested, just head to the link in the description to learn more. I hope you found this review useful, and I'll see you soon. People talk a lot about training ML models, but what does this actually mean? There's often a training dataset, and for simplicity, let's say our model predicts how tall someone will be based on their weight and height at age 10. The dataset could have thousands of people's weight and height at age 10, as well as their final height once they stop growing. And during training, the model learns a relationship in the training data. And there's an algorithm called gradient descent used for this. Let's quickly go over it. Now that the NPCs have clicked off the video, let's get into it. Gradient descent is used to minimize a function. Here's a simple function, y equals x squared. In calculus, and don't worry if you don't remember this, you might have taken its derivative, 2x, set it equal to 0, and you find x equals 0 is the minimum of the function. But for some functions, like the ones in machine learning models, it's just way too complicated to take the derivatives by hand. In some cases, it's even impossible. We need a different way to find the minimum. But why is minimizing a function even important for training models? It's because we want to minimize the error function, the error between the model's prediction for the final height and the true answer for all the people in our dataset. Let's build some intuition for how we might approximate the minimum of a function with efficient iterations. Here we have y equals x squared again, and let's say our initial guess for the minimum is x equals 3. We know the minimum is that x equals 0. What if we look at the slope of the function at x equals 3? This is the same as the derivative or the gradient. It's a positive number, meaning the function is increasing at this point. But if we want to get to the minimum of a function, we want to step in the opposite direction. Let's say our new guess is the old guess minus the slope times some step size, which I'll call alpha. For simplicity, let's say alpha is 0.1, but in practice we would use smaller values. Our new guess is then 3 minus 0.6, which gives us 2.4. We got closer to the answer of x equals 0. If we repeated this procedure for enough iterations, we would converge to the answer. What if our starting guess was negative 2? Here's the slope, the derivative is negative 4, and using the same formula, we get negative 2 plus 0.4 for a new guess of negative 1.6. Again, we got closer to our answer, and we would repeat this process. Here's the algorithm in pseudocode. So now we have some intuition for why this process works. You can try implementing it here and running your code against the test cases at the link in the description. For those who want a deeper understanding, there's actually a theorem that says if you're sitting at a point on a function and there's a bunch of directions you could travel in, the gradient gives the direction of greatest increase. So the negative of the gradient, which is exactly what we use, since we subtract out alpha times the gradient, gives us the direction of greatest decrease. Stepping in the direction of greatest decrease enough times gets us very close to the minimum of a function. So that's all it means to train a model. We're just iteratively minimizing the error function. What this error function actually is depends on the model we're training, and to learn more I recommend going through this list, starting with implementing gradient descent. Leave a comment for future video suggestions, and I'll see you soon. In this video, we're going to solve an ML programming question. We can read the problem and example test case on the left and write and run our code on the right. In case you're wondering, this programming question is part of a collaborative project between my colleague Nico and I. The problem asks us to implement the training loop for a linear regression model. We're first going to review linear regression, but here are a couple time codes if you want to skip this initial review. After we get through the problem, you'll be well prepared to dive into my machine learning roadmap, which you can secure for free at the link in the description. Let's get started. Linear regression is a simple statistical model that ends up being the foundation of neural networks. The goal is to predict an output y based on any number of input attributes. For each input attribute, we have a weight, symbolized by w, and we sometimes add a constant term b. These are called the model parameters. For this programming question, let's not worry about the constant term b. Each weight signifies how important the corresponding attribute is for determining the output y. We could think of x1 as the age of a presidential candidate, x2 is how many years they've served in politics, and x3 is how many laws they successfully created. And we can think of y as a predicted number of votes a candidate will receive. The parameters start off totally random, but over many iterations of training, they are adjusted to increase the model accuracy on the training dataset. The training dataset might look something like this, where we have x1, x2, x3, and the true y value for every row. Now let's talk a bit more about the training loop. The gradient descent update rule is used to update the parameters across many iterations. With each update or iteration, we slightly improve the model's accuracy. If you're unfamiliar with gradient descent, I strongly recommend checking out the video that's about to pop up in the top right. It's the first ML algorithm I think everyone should learn. The video is just 3 minutes long and provides an intuitive and visual explanation of training. If you are familiar with gradient descent, let's finish explaining the training loop and jump into the code. This equation tells us how to update each parameter at each iteration. Let's use it to update W1, W2, and W3 at each iteration. The learning rate, alpha, is given to us as input, but what about the derivatives? Fortunately, we don't have to calculate the derivatives by hand since I provided the getDerivative function beforehand. GetDerivative just requires us to pass in the model prediction for the current iteration as well as the desired weight, W1, W2, or W3. If you're wondering why the derivative depends on the model prediction, let's look at the error function. We can see that the error function depends on the model prediction from the current values of W1, W2, and W3. So it makes sense that the derivative of the error function also depends on the model prediction. Within the training loop, we will call getDerivative 3 different times and apply the update rule 3 different times as well. Let's jump into the code. First, let's set up our training loop. Let's get the model prediction using the function given. This function simply multiplies 2 matrices using NumPy's matmul function. If you're looking to learn NumPy and PyTorch, check the top link in the description. The good news is that the rest of this code doesn't require a deep understanding of NumPy or PyTorch. If we multiply the training dataset x by a vector of weights, we end up with a vector of all the model predictions, with 1 entry for each data point. Let's call getDerivative for each weight, noticing that this function follows 0 indexing. Let's then use the derivatives to update each weight based on the learning rate and the gradient descent equation. We can finish by rounding our answer to 5 decimal places, and our code passes the test cases. I hope you found this programming question useful, and if you're interested in a free and comprehensive package of lectures and programming questions, check out the machine learning roadmap at the top link in the description. Simply drop your email there to secure the roadmap. See you soon. Linear regression, a simple statistical model, is actually the first step to understanding neural networks in deep learning. The lowest levels of large language models, self-driving, and even deepfakes are a series of multiplications and additions. In this video, we'll review the basic concepts behind linear regression through a few quiz questions. Let's get started with question 1. Here's the main equation for linear regression for the case where we have 3 input attributes. We can think of x1 as the age of a presidential candidate, x2 is how many years they've served in politics, and x3 is how many laws they successfully created. We can think of y as the predicted number of votes a candidate will receive. What do the w's and the constant term b represent in linear regression? You can pause the video here if you need a moment to evaluate. The w's and b are referred to as learnable parameters for the model. They're learnable because they start off as random numbers, but over many iterations of training, their values are adjusted until we are satisfied with the model's accuracy on the training dataset, which might look something like this. Each row is a data point that has information for a particular year's election. We have the values of x1, x2, and x3, as well as the recorded historical value of the number of votes received. During training, the model finds the right values of the parameters that can capture the relationship in the data. Question 2. Which of the following is a valid example of linear regression? Here's choice 1, choice 2, choice 3, and choice 4. You can pause the video here if you need a moment to evaluate. The answer is actually choice 2. Even though the constant term or bias is set to 0, this is still a valid example of linear regression on a single input variable, x1. With the other answer choices, we're introducing nonlinearities in the parameters, which violates the main assumption of linear regression. Clearly, not all data in the world is linear, so linear regression isn't enough to build artificial intelligence. But there are still many cases where linear regression models perform well, and don't forget that neural networks are also built on top of linear regression. If you're looking for a quick beginner's guide to neural networks, check the second video in the description. Question 3. Which equation is used to calculate the error, also called the loss, for regression? During training, when we are improving the model's accuracy on the training dataset, we are actually minimizing the error between the model's prediction y and the true answers that are recorded. By the way, the gradient descent algorithm is used for that, and it's the first machine learning algorithm that I think everyone should learn. I have a 3-minute video breaking down gradient descent, and it's the third link in the description. But which equation is actually used to calculate the error? Do we average or sum up the errors? And do we square the errors or take the absolute value? You can pause the video here before the explanation starts. We wouldn't want positive and negative errors to cancel out, so we definitely have to use either the absolute value or the square. We'll go with the square to avoid issues with the absolute value function's derivative at x equals 0. And then we'll take the average so that the final error value isn't dependent on how many data points we have. The result is called the mean squared error function, and this is the standard loss function for regression. Question 4. Which matrix multiplication calculates the model's prediction for linear regression? You can pause the video here before the explanation starts. Based on the dimensions, choice A and choice B are actually undefined multiplications. Choice D is defined, but the output is a 3 by 3, and we're looking for a single number, y. Choice C gives us the exact equation we want, and if we were processing more than one data point, then we could simply add more rows to the first matrix, and the output vector would grow accordingly. NumPy and PyTorch are two libraries that are commonly used to implement these matrix multiplications as efficiently as possible. If you've made it to the end of the video, then you're probably interested in how to implement the concepts we talk about in these videos. I hope you found this review useful, and I'll see you soon. Okay, neural networks. Just give me 10 minutes and I will clearly explain how these work. No significant ML background required. And after you're done watching the video, there's a quick multiple choice quiz you can take in the description. Okay, let's say our goal is to predict how tall someone's going to be, so their final height once they're done growing. And we're going to use 3 pieces of information. Their parents' heights, so maybe like the average of their parents' heights, and then that's going to be one of our input variables, their current height, so whatever height this person currently is, and their current weight. So those input attributes, as they're called, are essentially our inputs in that first layer or first column in the neural network. And let's say x1 is like the average of your parent's height, x2 is your current height, and x3 is your current weight. So think of x1, x2, and x3 as literally being stored in those nodes. But what are all these edges, right? What are all these edges over here? And what are each of these hidden nodes in the next column doing? So to understand that, we need to quickly review linear regression, and we'll explain it in a pretty straightforward way. It's a concept from statistics that's used to build models that can make predictions. For our case here, where we have 3 input attributes, the formula for linear regression would be something like y equals w1 times x1 plus w2 times x2, and then a similar term for x3 plus some constant number b. And x1, x2, and x3 are our input attributes, and if y is our model's prediction, our output for however tall someone will be, based on x1, based on x2, and based on x3, then it makes sense that w1, w2, and w3 factor in how important each respective input attribute is. The higher w1 is in this formula, the more important x1 is, which actually, if you remember, is the average of our parent's height. That reflects how important that attribute is in influencing what y would be. But what about b, which stands for bias? This is analogous to the b in y equals mx plus b. It's kind of like a base height that we would always add on, since no one would ever have a height of 0. So if we think of this as a model to predict how tall someone will be, linear regression is actually the simplest machine learning model. It's the foundation for the rest of AI. We would actually start off this model with completely random weights. So W1, W2, W3, and B would be initially random. And then over some process called training, I know it can be really annoying when people refer to training a model and they're not really clear as to what this means. But just for now, let's treat training as a black box, and later on we'll clear up as to what it is. But at a high level, the process of training is simply adjusting or tweaking W1, W2, W3, and B until they're the right values, such that our model's predictions, the model's prediction is Y. We want Y to be as close to the true answer as possible, right? So we want our model's accuracy for predicting how tall someone will be to be as high as possible. Okay, we're finally ready to relate it back to the neural network and our hidden nodes over here. So it turns out that each of these nodes, this node over here, as well as the 3 below it, are each performing linear regression. Each of these nodes are actually calculating some output Y based on the X1, X2, and X3 that come in the previous layer. So each of these nodes independently is actually learning a W1, a W2, a W3, and a B. But at this point in the model, before we even consider what this output layer is doing, for some given person we passed into this network, right? We passed in their input features, their input attributes, their X1, X2, and X3, though those pieces of information about them that ultimately will affect how tall they will grow. At this point in the network, in our hidden layer, remember we're going through the network from left to right, and in our hidden layer, we have 4 numbers for that person, Y1 through Y4. But we want to predict one final number, right? That is going to be the model's prediction for how tall someone is. So our next layer actually has less nodes. We only have 2 nodes, and we can think of the number that is ultimately calculated in that node to be O1 and O2 for output 1 and output 2. Just as in the previous layer, O1 is calculated using our linear regression formula, except this time it has to factor in Y1 all the way through Y4. So we have an additional W4. We don't just have W1 through W3, we also have W4, and of course we have our constant term B. O2 is calculated the same way using Y1 through Y4, but we should remember that W1 through W4 as well as B for O2 for that node are learned completely separately. So these 2 nodes are operating completely independently. If the point of this neural network is to predict how tall someone's going to be, then we wanted just one output number. So we might do something like this. We average O1 and O2, and that output is the model's prediction. So then the process of training this neural network to increase its accuracy based on some training data set where we may have a bunch of people and we have their input information. For every person in this data set, we have what their X1, X2, and X3 are, and we know what their ultimate height ended up being. This is the data set that the model would learn from. The process of training then is just the model figuring out what W1, W2, W3, and B should be for this node, as well as the 3 nodes below it, and figuring out what W1 all the way through W4 as well as B should be for O1 and O2 for those nodes. The ultimate goal of training, and we're just treating training as a black box for now, but the ultimate goal is to increase the model's accuracy on that training data set, and hopefully the model gives pretty good predictions later on for people it's never seen before when we pass in their input information. So that's the general idea of neural networks, but there's still a few things left to talk about. There is something called a nonlinearity function, such as the sigmoid function. These are essential for neural networks to perform better than other AI models, so definitely leave a comment if you'd be interested in a video on nonlinearities. And then training, right? We don't want to just treat training as a black box. What's actually happening there? It turns out that there is a simple formula, just a math formula, that explains how AI models are trained. And this is called gradient descent. And here's the formula. It's that the new weight, right? So we had those W1s, W2s, even the Bs. This formula applies for any one of those parameters of the model, as they're called. The new weight is equal to the old weight minus some number called alpha, which might be like 0.01 or 0.001, times a derivative from calculus, actually. And then this formula is basically applied iteratively over and over again inside a for loop until we have the right values for all our w's and b's so that the model's accuracy is strong enough. And I've got a 5-minute video going into more detail about this formula. That video is linked in the description. Lastly, you might be wondering how to implement this concept, right? How would you code this up in some sort of language like Python, which is typically used for ML? If you're interested in a video where I code up neural networks from scratch, definitely leave a comment as well. If you like my style of teaching, be sure to subscribe, and I'll see you soon. Neural networks. Before you start coding them up, it's important to be familiar with the basics. So let's go over a few multiple choice quiz questions. Then at the end, there are even more practice problems that you can try. And if you need a quick refresher on the basics of neural networks before we go through the quiz, check out the second link in the description. Let's get started. Question 1. You may have heard that GPT-3 has over 100 billion parameters across its many subnetworks. How many parameters does this simple model have? Remember, a parameter is either a weight or a bias. If you want to try calculating the answer on your own, I recommend pausing here. Okay, here's the explanation. So in this equation, there are 3 weights and 1 bias, or 4 parameters. And let's go layer by layer. The first layer is the input layer, which doesn't contain any parameters. Each node simply contains one of the input attributes, x1, x2, and x3. The next layer is where the parameters begin. Since each hidden node is connected to each of the 3 input nodes, that means that each hidden node uses this equation to calculate a number y. That's 4 parameters per equation, and we have 4 nodes, so that gives us 16 parameters in this layer. Finally, the output layer. Each output node is connected to each of the 4 hidden nodes, so each output node uses this equation to calculate a number O. There's 5 parameters in this equation, and we have 2 nodes, so that gives us 10 more parameters. This neural network has 26 parameters in total. Question 2. Let's say we want to create a neural network that could predict the probability that the next word in a live stream should be censored. Also, let's say that the network should factor in the previous 3 words. Here's option 1, here's option 2, here's option 3, and here's option 4. The answer is option 4. The internals of the network actually don't matter for this question. We want a network with 3 input nodes, 1 for each word, and a single output node, since the network outputs one final number in the form of a probability. Question 3. Let's say we want to store the weights of a layer inside a matrix. Let's consider this equation. The input data point can be represented by this vector, and the weight matrix can be represented by this matrix. The product of the weights and the input vector plus the bias, which could simply be stored in a separate variable, gives us the output we want. So how many matrices and what shapes would be needed to store all the weights for this model? And let's not worry about biases. Option 1, a 4x3 matrix and a 2x4 matrix. Option 2, a 4x2 matrix and a 4x4 matrix. Option 3, a 3x2 matrix and a 2x4 matrix. Option 4, a 3x3 matrix and a 4x4 matrix. If you want to try calculating the answer on your own, I recommend pausing here. Okay, we'll go layer by layer again. The input layer doesn't contain any weights, so we can move on to the hidden layer. The hidden layer has 4 nodes, and each node stores a W1, W2, and W3. That's 3 weights, so our first matrix should be a 4x3 matrix. Assuming the input vector is a 3x1 vector, this allows the matrix multiplication to work out, and we would end up with a 4x1 vector, which is exactly what we want. Each entry in that vector corresponds to a y value in a hidden node. In terms of the actual multiplication, we would multiply this row by this column to get this value, and then this row by this column to get this value, and so on. Finally, the output layer. We have 2 output nodes, and each stores 4 weights, W1 through W4, so we would need a 2x4 matrix. That means that option 1 is the correct answer. Question 4. Between layers, we often plug values from the neural network into nonlinearities like the sigmoid. Its outputs are always between 0 and 1, and the greater the input, the closer the output is to 1. There are multiple benefits to using the sigmoid, and other nonlinearities like the tanh function. But let's say we had a neural network for predicting whether someone develops diabetes, and we added the sigmoid after the final layer. What would be the purpose of this? Option 1, perform regression instead of classification. Option 2, ensure the model outputs a probability. Option 3, simplify derivatives for gradient descent. And option 4, improve runtime since sigmoid calculations are actually easier on GPUs. The answer is option 2. Since the output is between 0 and 1, we can call it a probability. Option 1 is incorrect. We want to classify every input person as diabetic or non-diabetic, not perform regression. An example of regression would be a model that predicts how tall someone would be after they're finished growing. Option 3 is incorrect as well. This doesn't simplify derivatives for gradient descent, it actually makes them more complex. And option 4 is actually just irrelevant here. And that concludes our neural networks quiz. If you've made it to the end of the video, then I think you're the right fit for our ML community. But first, I would recommend checking out some more practice problems, which you can grab from the link in the description. I've actually created a full course on LLMs with over 25 concise modules. It will always be free, and you can secure it using the link in the description. I hope you found this video useful, and I'll see you soon. In this video, we're going to solve an ML programming question. We can read and write the problem in an example test case on the left, and write and run our code on the right. In case you're wondering, this programming question is part of a collaborative project between my colleague Nicode and I. The question asks us to implement a model that can classify black and white images of handwritten digits into the correct category. If you're not familiar with neural networks or the PyTorch library, don't worry, we'll do a quick review of both. If you are familiar with those topics, you can skip to this time code. It's also in the description if you ever want to skip around. Let's get started. First, a brief review of neural networks. For a more detailed review of neural networks, check the description of this video. Otherwise, let's get into it. Let's say we're building a model that predicts one final number, the number of votes a presidential candidate will receive. We'll assume that we have a training dataset with 3 input attributes per row. X1 is the age of a presidential candidate, X2 is how many years they've served in politics, and X3 is how many laws they successfully created. We also have a label for every data point, which is the recorded historical value of how many votes that candidate received. We want the model to learn to predict this number well. The neural network stores X1, X2, and X3 in the first column of nodes, and each node in the hidden layer is fully connected to each of the 3 inputs. That means that each hidden node is performing linear regression based on this equation. Each hidden node learns W1 through W3 plus a constant B so that each hidden node can predict a number Y. We don't need to worry about the interpretation of these numbers, and we can think of them as internal to the model. The truth is, though, that each node is learning something unique about our dataset that helps inform the final prediction. The last node takes Y1 through Y4 as input and calculates the output O based on this equation. O is the model's prediction for votes received. Across many training iterations, the values for all the W's and B's are adjusted until the model's predictions achieve a high enough accuracy. That's the general idea of a neural network. If any part of that explanation was confusing, I still recommend watching the rest of this video first, and then checking out the 10-minute neural network video linked in the description. Let's get started with the implementation. While we're writing the code, I'll point out and go over the PyTorch specific details as well. First, the problem description. We're asked to use an initial layer with 512 neurons as opposed to only 4 in the example we had. Side note, this number is arbitrary, but the larger it is, the more the model can learn. We'll use a ReLU activation and a dropout layer, and if you're not familiar with those, don't worry, we'll briefly go over those later in the video as well. The final layer should have 10 neurons and a sigmoid activation. In our previous example, we were only predicting one final number, so 1 neuron was enough. But in this case, we want to predict 10 numbers, where each is a probability between 0 and 1, reflecting the chance that the input image passed in belongs to a particular category. The sigmoid function looks like this, and its outputs are always between 0 and 1. The greater the input, the closer the output is to 1. We pass all 10 output numbers into the sigmoid function before returning the final model prediction to ensure that the model's outputs are always between 0 and 1. But what about the input? Instead of 3 attributes about a presidential candidate, we're dealing with 28 by 28 images where we have a number at every pixel. Fortunately, the input passed in is already squashed into a one-dimensional vector with length 28 times 28, or 784. This means that the input layer to our neural net stores 784 numbers. We'll write the constructor to our class where we define the architecture as well as the forward method, which returns the model's predictions for images passed in. Okay, first the constructor. The way we declare a standard layer in PyTorch is with nn.linear, which takes in the number of nodes in the previous layer and the number of nodes in the current layer being declared. That means we'll start by defining the hidden layer, since no layer precedes the input layer. There's 784 input nodes and 512 hidden nodes. We'll pass all 512 hidden values into the ReLU function next. 15-second crash course on ReLU. This function outputs 0 if the input is negative and outputs the input value otherwise. Introducing nonlinear functions like the ReLU between neural network layers helps the model learn more complex relationships as opposed to simple linear relationships. Next, we'll declare a dropout layer with probability equal to 0.2 or 20%. 30-second crash course on dropout. This means that each of the 512 values outputted by the ReLU function have a 20% chance of being erased and set to 0. So on average, 20% of the nodes will be effectively erased. This might seem counterintuitive since we said that the more nodes we have in this hidden layer, the more the model can learn. However, if we have too many nodes, then the model will have too many parameters, since each node adds 785 more parameters from the 784 W's and the one constant term B. Models with too many parameters tend to perform poorly on images that were not encountered during training, since all those extra parameters cause the model to memorize irrelevant noise in the training data. So we choose 20% of them at random every time the model is called and effectively delete them. Time for the final output layer, which gives us the model prediction of 10 probabilities. And lastly, the sigmoid. The forward method will be straightforward. All of the layers declared above are also subclasses of nn.module, which means that those classes have a forward method of their own that we can call. Our forward method just requires passing the input images from left to right through the layers of the neural network. Let's round our answer to 4 decimal places, submit our code, and see that we passed the test cases. There were a lot of concepts packed into this video, so congratulations on making it to the end. If you have any questions, I recommend picking one of the other videos linked in the description, which go into these subtopics in more detail. Since you've made it to the end of the video, you might enjoy our ML community, where I offer weekly lectures, one-on-one mentorship, and a few other surprise bonuses. Simply drop your email at the link in the description to learn more. See you soon. Okay, in this video, we're going to cover the main concepts of PyTorch, a deep learning library. This video doesn't require any machine learning or deep learning experience, since we'll quickly review the basic concepts. If you have ML experience and want to skip directly to PyTorch, I'll provide the time codes before the ML review starts. PyTorch is used to build and train neural networks and is the industry standard for deep learning, rather than TensorFlow. PyTorch also calculates all derivatives necessary to train a neural network for us so that we avoid math by hand. Lastly, implementing concepts in PyTorch will reinforce your understanding. I think that anyone interested in ML should learn the basics of PyTorch, and this video is the best place to start. Let's begin. The main data structure of PyTorch is a tensor. Tensors are like multi-dimensional arrays that also store other attributes, such as the grad property, which contains derivatives necessary to train models. If you're unfamiliar with why derivatives from calculus are necessary to train models, don't worry, that isn't required knowledge for this video. After this video, I recommend watching my 3-minute explanation of gradient descent, the algorithm that uses derivatives to train models. It's the first ML algorithm I think everyone should learn. Back to tensors. We can create tensors from Python lists, whether those are one-dimensional lists, two-dimensional lists, or greater. We can also create tensors of all ones or all zeros, and we just have to specify the shape. Once we have data stored in tensors, we call functions like sum and mean. We might be interested in summing across the rows or columns, or finding the average of each row or column. Small clarification. The dim parameter is set to 0 when we want to find the sum of each column, and is set to 1 when we want to find the sum of each row. That might seem a bit counterintuitive, but it's important to remember. Lastly, we can add two tensors together like this, and multiply corresponding elements like this. Okay, but PyTorch is supposed to be for building and training neural networks. Let's briefly review neural networks, and if you want to skip this review, here's the timecode. It's also in the description if you want to skip around. Let's say we're building a model that predicts one final number, the number of votes a presidential candidate will receive. We'll assume that we have a training dataset with 3 input attributes per row. X1 is the age of a presidential candidate, X2 is how many years they've served in politics, and X3 is how many laws they successfully created. We also have a label for every data point, which is the recorded historical value of how many votes that candidate received. We want the model to learn to predict this number well. The neural network stores X1, X2, and X3 in the first column of nodes, and each node in the hidden layer is fully connected to each of the 3 inputs. That means that each hidden node is performing linear regression based on this equation. Each hidden node learns W1 through W3 plus a constant b so that each hidden node can predict a number y. During this learning phase, the values of the w's and b's are adjusted until we're satisfied with the model's accuracy. The gradient descent algorithm mentioned earlier is used here. We'll also talk about how to implement a PyTorch training loop at a high level later on in the video. The last node takes y1 through y4 as input and calculates the output O based on this equation. O is the model's prediction for votes received, and this node learns W1 through W4 as well as a constant b. That's the general idea of a neural net. If any part of that explanation was confusing, I still recommend watching the rest of this video first, and then checking out the 10-minute neural network video linked in the description. Okay, now let's talk about how to code up a diagram like this in a PyTorch class. Every PyTorch model or module we define is a subclass of nn.module, where nn stands for neural net. In the constructor or the init function, we define the different layers of the neural net and how many nodes will be in each layer. Every PyTorch model is required to define a forward function that takes in an input vector and passes it through the layers of the network, returning the model's prediction. For the constructor, there are a few pre-built layers in PyTorch that we can make use of. The first is nn.linear for defining a standard linear regression-based hidden layer. We just have to specify the number of nodes in the previous layer and the number of nodes in the current layer being defined. That means we can declare the hidden layer of this diagram with this line of code, and we can declare the output layer of this diagram with this line of code. There's no need to define the input layer, since we're going to simply call the forward method of the hidden layer and pass the input vector in. But neural networks are more than just nodes that perform linear regression. They also contain nonlinear functions between each layer, like the sigmoid and the ReLU. We'll focus on the sigmoid function for now. The smaller the input, the closer the output is to 0, and the larger the input, the closer the output is to 1. Adding nonlinear functions like the sigmoid between linear layers lets the model learn more complex relationships, since we know that most data isn't strictly linear. To be clear, this means that we would pass each of the 4 hidden values, y1 through y4, into the sigmoid function before passing them into the output layer. Within the constructor, we just have to define nn.sigmoid. We will call its forward method within the forward method for this class. Just to be totally clear, the forward method for our nn.sigmoid instance is just transforming the input to numbers between 0 and 1 based on this function's equation. We can quickly write the forward method for our class like so, and now that we have our model defined, we can make an instance and start to train it. Before any training, the model stores random numbers for all the weights and constant terms in the network, so its predictions won't be accurate. But over training, gradient descent is used to update the network's parameters. The actual training loop requires understanding gradient descent and a few other details, so I saved the code for a different video, which should pop up in the top right. But at a high level, the pseudocode for training loops looks like this. Get the model's prediction based on the current parameter values, calculate the model's error based on the true answers listed in the dataset, and adjust the values of the parameters so that on the next iteration, the error is slightly less. If you're looking to learn more, I have a few recommendations. If you prefer YouTube videos, the gradient descent video is the best place to start if you're unfamiliar with this algorithm. I also have a more detailed video on neural networks and a corresponding quiz video where we go over a few multiple choice questions. If you're interested in my comprehensive machine learning roadmap that works all the way up to implementing a GPT in PyTorch, you can secure it for free at the top link in the description. Lastly, for those interested in one-on-one mentorship, I offer an ML community, which you can also learn about from the top link in the description. I hope you found this PyTorch intro useful, and I'll see you soon. In this video, we're going to solve an ML programming question. We can read the problem and an example test case on the left and write and run our code on the right. In case you're wondering, this programming question is part of a collaborative project between my colleague NeetCode and I. When training NLP or natural language processing models, we have to represent words as numbers. That way, we can pass sequences of words into models and the calculations can be performed. In the case of a sentiment analysis model, we pass in text, first breaking it up into a series of numbers, and the output is a binary category like positive or negative emotion. In the case of an LLM, the output is the word that's most likely to come next in the sequence. Then we concatenate this word to the initial input and call the model again, and that's how the response is generated. Either way, the initial data processing to train both types of models is actually identical. This process of splitting up a body of text into words, characters, or some combination of the two, and then mapping each token to an integer is called tokenization. Let's get into the problem. We'll start by going over a basic test case. We have two inputs to the function we have to write. The first is a list of strings, each with positive emotion. The second is another list of strings, each with negative emotion. This simple example has just one string per list. Side note, these sentences are just some dummy examples I came up with, but they could be tweets that are fed into a model that outputs the sentiment as a number. We could then use these numbers to inform a trading algorithm that buys or sells a particular stock based on how people feel about it on Twitter. By the way, apparently likes really help with the YouTube algorithm, so if you're enjoying the video, it would be great if you hit like. Back to the test case. Here's the output, which consists of two different lists. We have one number for each word in the input. The word I maps to 2, the word will maps to 9, the word short maps to 5, and so on. The same logic holds for the positive sentence, except we pad the list at the end with a 0 so that both lists can be the same length. But where do these numbers come from? The problem description tells us that we should follow lexicographical order. Alphabetically, the first word should be represented as 1, the second word should be represented as 2, and so on. This is a convention that is followed for training many NLP models. We have to represent each token as a number, so why don't we arbitrarily just choose to create the mapping in alphabetical order? Once the sequence is passed into the model, the neural network starts learning vector representations for each word, which actually encode the meaning of the word, unlike our initial alphabetical assignment. By the way, check out the second link in the description if you're interested in a simple explanation of neural networks, but don't worry, the remainder of this video doesn't require knowledge of neural nets. Back to the test case. From this example, we can gather that the main goal of this function is to actually generate a mapping of words to integers. Once that mapping is created, we can just fetch the integer for each word and place it in the output list. Oh, and don't forget that we need to pad the shorter sequences with a 0, just like in this list over here. Let's start writing the code. Okay, our first goal is to get all the unique words from the input sequences in a single list. Why does this help us achieve our goal? Because if we just sort this list of strings based on alphabetical order using Python's sort function, then our mapping is actually complete. Here's why. In the sorted version of the list, the word at index 0 should be mapped to 1, the word at index 1 should be mapped to 2, and so on. Okay, so the goal is to get all the unique words from the input sentences into a single list. Also, we don't want any duplicate words in this list. Here's why. In the example test case we looked at, there were no duplicate words, but the same word can definitely come up more than once when training a model on a large dataset. In that case, we don't want the duplicates of the word to show up in the sorted list. since all occurrences of that word should have the same index mapping. To get rid of duplicates, we can use the set data structure, which is actually a hash set. If you're rusty on data structures, don't worry, this example is not terribly complex. Let's simply declare the set. Combine both input lists together, iterate through each sentence in that combined list, iterate through each word in the sentence where we call split to break up the sentence based on spaces, and add each word to the set, which will automatically ignore duplicates. Now we can just convert the set to a list and sort it. Now that we have this mapping created, we can easily create the output lists. Let's define a list that will contain all the lists of integers. Let's iterate through each sentence again. Let's define a list of integers, iterate through each word, and append the corresponding integer for that word, which can be found by indexing into the dictionary. So there is actually one more step we needed, and now it should make sense as to why. We want to fetch the corresponding integer for each word, but the sorted word list we created doesn't let us efficiently accomplish that. We don't want to search through the whole list every time we need to find the corresponding integer for a word. So before the code block that begins on line 16, let's build a dictionary, since we can query a dictionary much faster. Iterate over the sorted word list, define a counter, assign the current integer to the word in the dictionary, and increment the counter. Now, this line of code should make sense. Once we're finished with a sentence, we append the sequence of numbers to the overall list. But we still have to take care of the padding. Fortunately, there's a simple PyTorch function that will take care of that. I'll link my Intro to PyTorch video in the description for those looking to learn this library. All we have to do is ensure that each list of integers is actually a tensor, the main data type in PyTorch. Lastly, we can return the result of the padding function, which will use zeros for padding by default. All we have to specify is batch first equals true, which means that the first dimension in the output will be the total number of sentences n, and the second dimension in the output will be the length of the longest sentence t. If batch first was false, then the output would be t by n, which isn't what we want. We can submit our code and see that it works. We just implemented basic tokenization. If you made it to the end of the video, then you're the kind of person who might enjoy our ML community, which you can read about at the link in the description. Simply drop your email there to learn more, and I'll also send over more free lectures and ML resources. See you soon. NLP, or Natural Language Processing, is the field of ML focused on teaching AI to read and write like humans. With the development of the transformer, AI-generated text is almost indistinguishable from humans. But before diving into transformers, there are some NLP fundamentals that are essential to understand. This video will go over 3 quiz questions that cover these fundamentals. We'll cover tokenization, the process of breaking up a string into a series of characters, words, or subwords, also known as tokens. We'll also cover word embeddings, which are vector representations for each token. After you go through this quiz, you'll be well prepared to start my machine learning roadmap, which is completely free and available at the top link in the description. Let's get started with question 1. Here is an example of a model vocabulary. The vocabulary is just a set of all the unique words the model encounters within the training body of text. Side note, the training body of text for ChatGPT is essentially the entire internet, while the training body of text for a sentiment analysis model, which is an emotion predictor model, might be a series of movie reviews and a corresponding label for each sentence. We can see that for every token in the vocabulary, there is a corresponding integer. When passing text into the model, each token is encoded with its assigned integer. The model is actually generating numbers, and we decode the integers back into the corresponding tokens. But how are the integer assignments for each token learned? A. No learning necessary. They're arbitrarily assigned at the start of training and kept constant throughout. B. They're randomly initialized but changed during training as the model learns which integers best encode each token. C. They're initialized based on the initial embedding representations and kept constant forever. D. No learning necessary. Each time the model is called during training or testing, we randomly reassign the integers. The answer is A. No learning necessary. They're arbitrarily assigned and kept constant. We need the integer assignments to be consistent so that we can decode the model's output back into coherent strings. But the way we assign them can be completely arbitrary as long as we keep the mapping constant. But that means that the integer encodings carry no information about the actual meaning of each word. and it's important for the model to understand the meaning of each word when predicting the emotion in a sentence or generating a response to our prompt. That's where embedding vectors come into the picture, which we'll talk about in question 3. Okay, question 2. Here's an example of character level tokenization, and here's word level tokenization. Which of the following is an effect of using character level over word level? The answer is B. The model vocabulary will be smaller, but diversity will be greater. If we use word level tokenization, the vocabulary might be the set of all words in a language. But if we use character level tokenization, the vocabulary would just be the set of all characters in the alphabet plus the special characters, but that's still far less than the number of words there could be. So, the vocabulary would be smaller. And for a model where we generate one character at a time, there are actually many combinations or paths the model could take every time the next character is chosen. In contrast, with a word level model, the entire next word is chosen each time the model is called, so the responses tend to be less diverse. Okay, question 3. How are these vectors learned? Here's a quick summary of embeddings. There are vector representations for words that also encode meaning. Similar words will have representations that are closer to each other when visualized, and unrelated words will be farther apart. Also, the dimension of each vector here is only 2, but in practice, it could be in the thousands. When passing a sequence of text into a model, the first step in the calculations for the output is to fetch the embedding vectors for each word. We can think of this like a lookup table from the token integers to vectors. Once the embedding vectors are retrieved, a series of multiplications, additions, and nonlinear functions are used to form the final output. Back to the question, how are these vectors learned? The answer is that they're randomly initialized, and over many iterations of training, the gradient descent rule is used to update the embedding vectors. This means that initially, words that are entirely unrelated may be very close to each other, and words that are related may be far apart, but over training these vectors are updated. Gradient descent is the training algorithm, and it makes use of some very basic calculus. My 3-minute video breaking down the equation is linked in the description for those looking to understand it deeply. That wraps up our brief review of tokenization and embeddings. If you're interested in how to implement basic tokenization in Python, I'll also link that video in the description. Okay, if you've made it to this part of the video, then I think you'll enjoy our ML community. I offer weekly lectures, one-on-one mentorship, and a few special bonuses. If you're interested, just head to the link in the description to learn more. I hope you found this review useful, and I'll see you soon. In this video, we're going to solve this machine learning programming question. It's part of a collaborative project between my colleague Navdeep and I. We'll go over the description and a basic test case on the left and solve the problem on the right. The problem is titled GPT Dataset. For large language models, like ChatGPT, a very special kind of dataset is used for training. This programming problem asks us to build and return that dataset. Let's go over the concepts behind this problem before jumping into the code. You've probably heard that LLMs are trained on the entire internet, and this is true. We can simply feed in massive chunks of text into the model, and there's no need to label each sentence or paragraph. This is different than if we train, say, a sentiment analysis model that classifies each input sentence as positive or negative. The dataset to train a sentiment analysis model would consist of sentences where every data point is labeled as positive or negative. So that's the good news. To train an LLM, we don't need to label any data. We can effectively just feed the raw text into the model. And then during training, if we passed in this giant block of text, the model learns to predict the next word in the sequence for every possible context. So the model learns that after the context cricket, the word is can come next. The model learns that after the context cricket is, the word a can come next. The model learns that after the context cricket is a, the phrase bat and ball can come next, and so on. The way LLMs learn to read and write in a language is by memorizing all the likely sequences of words that can come up. They're effectively just large autocomplete models that can predict what word comes next in a sequence extremely well. When we actually prompt the LLM, it generates the response one word at a time based on what's most likely to come next. Formally, we would say that the neural network is learning a probability distribution over the entire language. But don't worry, this video doesn't require a background in neural networks or probability. Okay, so why does this programming question even exist? Why can't we just feed in the entire dataset as one long sequence into the model for training? It's because of a limitation in the transformer architecture known as context length. To summarize, there's a maximum number of words that an LLM can remember or process at once. The LLM forgets, or more accurately, cannot factor words that are outside of this window into its prediction. The context length is a hyperparameter for training an LLM, meaning that we decide its value before training the model. GPT-4 has a context length of 32,000 words, and the code that we'll write at the end of this video will depend on the context length passed in. So at every iteration of training, we want to select a random sequence from the entire, very large training dataset and have the model memorize the different autocomplete sequences within it. One more clarification. To make training more efficient, we don't just pass in one random sequence at every iteration, we actually pass in multiple of them. The batch size hyperparameter tells us how many sequences the model will learn from at each iteration. Those batch size different sequences have nothing to do with each other. They're completely independent, and the model learns from them in parallel. Okay, now we're ready to jump into the code. Small side note, if you're enjoying the video, it'd be great if you hit like so that YouTube can recommend more of these videos to you. Back to the code. This function would be called at every iteration of training to generate the batch. Let's take a quick look at the example test case. The raw dataset, context length, and batch size are provided to us. We have to return x and y, where both x and y have length equal to the batch size of 2. The first entry in x corresponds to the first entry in y, and the second entry in x corresponds to the second entry in y. The first random sequence chosen is darkness my old. We know that my follows darkness, old follows my, and friend follows old. The same logic applies to the second random sequence chosen. Okay, the first step is to split the input string into a list of words, since we're operating on a word level. Next, we want to randomly generate batch-sized different starting indices. That way, we can simply grab the context length words that follow from each starting index. We'll use PyTorch's randint function. If you're looking to learn PyTorch, I have a couple Intro to PyTorch videos already uploaded, and I'll be releasing a more visual, animated tutorial in a few days. But the good news is that making this function call won't require significant PyTorch knowledge. We just need to specify the highest random number that could be chosen as a starting index. That should be the number of words minus the context length, and this range is exclusive of that number so that we don't go out of bounds from the dataset. So let's specify low and high, and also specify how many random numbers we want to select. Lastly, let's convert the returned tensor to a normal Python list. Next, we simply need to grab the sequences x and y. We'll set up the lists, iterate over all the starting indices, index out a sequence to store in x, index out a sequence to store in y, which is effectively the same sequence, just shifted one unit over since y contains the words that need to be predicted via autocomplete. Append those to x and y, and we're finished. Our code passes the test cases as well. And that's the explanation and solution to GPT dataset. If you made it to the end of the video, you might enjoy the ML community. Just drop your email at the link in the description to learn more about it and receive more free ML resources. I hope you found this programming question useful, and I'll see you soon. Chatbots in recent years have been alright, but now we have ChatGPT. So what makes these newer models so effective at reading and writing like humans? It's a concept called self-attention. A Google search of this topic gives some confusing diagrams and equations, so let's break that down. I'll take the first few minutes of the video to give a high-level overview, and then after that, I'll make a second pass through the explanation, but the second time I'll add more of the math and dive even deeper. So let's consider these LLMs or GPTs as a black box. We know they take in some sequence of words like an instruction or a question and they output the response. But the way the response is generated is actually word by word. So the next word is generated, concatenated, the model is then called again, and so on. And inside this black box, the model is doing a ton of math to ultimately make its prediction for the next word in the sequence. To get some inspiration for teaching computers to read, let's think about how humans read. Do we read each word completely independently, not considering its relation to the words that came before it? No, we read word by word, and each word has some relationship with the word that came before it. When we get to a noun, we realize it's the subject being described by the adjective that came before it. Or when we get to a question mark, we realize that a question was being asked based on a previous word like how, why, or what. We subconsciously consider the relationships between the different words in a sentence in order to totally understand it, rather than looking at words independently. But how does a model do this? For an input sequence of length t, so t different words, the model calculates a t by t matrix of attention scores, where each entry signifies how strongly associated two words are with each other. For example, the word how can be used in the sentence, "How are you?" or the sentence, "This is how you write." The word how has a slightly different meaning depending on the context, and we see a relatively high score for the connection between how and the question mark, indicating that how is used a particular way in this sentence. Once the model has this matrix, it knows how important each word is to the previous words, and it can do some calculations to predict the next word. But here's the crazy part. I know it can be really annoying when people treat training as a black box, but this video would simply be too long if we also went into how training works. So for a 5-minute intro to training, check out the video in the top right. And for now, we can just treat training or learning as some iterative process where the model gets better at its task of predicting the next word. But the crazy part is that during training, the model develops some complex math formula to calculate the entries of this matrix for the future sentences that will be passed in. The formula is learned from the data it's trained on, which is typically a massive body of text like Wikipedia fed into the model during training. So that's the high-level overview of attention. The model learns to calculate a number, signifying the affinity of every pair of words, which helps it accurately predict what comes next. Now let's dive deeper and make a second pass through this explanation. This time, we won't leave out the math involved in calculating this really important attention matrix. The main idea is that we want the words in a sentence to talk to each other and figure out which ones they should associate with. For example, we want the adjectives and the nouns they describe to seek each other out and associate, ultimately resulting in a high attention score. The way we do this is by having every word emit two vectors, a key and a query. I've only shown it for 2 words here, but every word emits its own key and query. A word's query vector represents what it's searching for or querying for, and a word's key vector represents what it has to offer or what the information actually stores or encodes. If a noun is searching for the adjective that describes it, then its query might align with the adjective's key. Then we just take the dot product between every word's query with every other word's key, and those values populate the attention matrix. Remember that the dot product between two vectors is a measure of similarity. The higher the output, the closer two vectors are to each other. But how do you actually calculate the query and key vectors for every word? Linear regression. A simple, single-layer neural network is used. Before a sequence of words is passed into the attention layer, we have every word represented as an embedding vector. So we have one linear network that takes in the embeddings for each word and outputs the query vectors, and another linear network that also takes in the embeddings but outputs the key vectors. Remember that each of the nodes in a neural network is just performing a linear regression based on this equation. Each node operates independently of the others and learns its weights through training. For a 10-minute refresher on neural networks, just check out this video. So now we've calculated the attention matrix. This T by T matrix is actually the crux of how LLMs read and write. There is one part still left to discuss though. In addition to key and query vectors, another linear network calculates a value vector that is emitted by every word. We then multiply the attention matrix by the matrix of value vectors for every word, and this is the actual output of the attention layer. If the key is what information a word has or encodes, let's think of the value as what's actually relevant for the word to share, what it actually exposes. So let's see what happens in this matrix multiplication. If this row is multiplied by this column to yield this value, and if this row is multiplied by this column to yield this value, and so on, we can see that we're taking a weighted average of the words from the past to end up with a new and transformed vector for this word. And we end up with a new and transformed vector for every word. So the ultimate output of the attention layer then is actually the model's refined interpretation of the meaning of every word, far more nuanced than the crude embeddings that were passed in. The model has factored in the context of neighboring words to generate a new representation of each word, ultimately culminating in the model accurately predicting the next word. If you found this video helpful and are interested in more videos breaking down the transformer, leave a comment and I'll see you soon.